The purpose of this video is to discuss the scientific method, which is how chemists study matter and the energy associated with it. After this class, you'll be able to describe the scientific method, apply the scientific method to a given observation, define some terms, explain the difference between a law and a theory, an independent and a dependent variable, as well as a confounding variable. You'll also be able to describe the difference between supporting and proving a hypothesis. What is the scientific method? Yes, the scientific method is a way of understanding the world based on observation and experimentation. The scientific method is a logical process that one can follow when they're wondering why or how something works. Now, I'm sure you've learned about the scientific method before, so now's a good time for you to pause and try to list the steps of the scientific method. Okay, so diagram or list the steps of the scientific method. Please pause and do this. I have typed them out so I don't have to list them, but these are the steps of the scientific method. So the very first step is not making a hypothesis. The first and most important step of the scientific method is to make an observation. Then once this observation has been made, we should ask a question. So why or how, for example. Then we should do background research because someone has probably wondered something similar and maybe already conducted some experiments on this topic. So the step 3 here is to figure out what others already know. So do a literature search. Once we've done the background research, then it is time to propose a hypothesis. A hypothesis is a plausible explanation based on the existing evidence, so based on what was learned in the literature search. Ideally, the hypothesis is falsifiable, which means that it can be proven wrong. Once the hypothesis is developed, one should design an experiment to test that hypothesis, then conduct the experiment and evaluate the results. So was the hypothesis supported? Now, it's very important to point out that we and no one will be proving hypotheses. Hypotheses are not proved. Scientists can't know anything for certain, but their experiments can support their explanations. Now, if the hypothesis was supported, what should you do? Well, the scientists should communicate with other scientists. Recall that literature search that we did at the beginning when we were developing our hypothesis. Once a scientist has conducted an experiment, they should add to the literature so other scientists can learn from their experiments. Not only do we want other scientists to learn from our experiments, we want other scientists to try to reproduce our results. Our results should be reproducible. And once you've added what you've learned, you've communicated with other scientists, you've added that information to the literature, that gives other scientists the opportunity to try to reproduce your results. If the hypothesis was not supported, well, there's a couple of things that could be going on. So the scientists should review the findings. It's possible that the hypothesis was just wrong. It was incorrect. So try again. Revise your hypothesis, figure out another plausible explanation that could be for your observation, and design a new experiment. Or you might need to review your experimental design and make sure there aren't any unaccounted for variables. The best way to learn the scientific method is to apply it. And so we're going to be doing that. I will lead you through applying the scientific method to an observation in just a moment, but you yourself will also work with a team to apply the scientific method to an observation that you have made recently. You will try to apply the scientific method to just any observation that you've made recently. I will try now to apply the scientific method to a chemistry observation. So one might notice that when a shiny strip of metal, this is magnesium metal, is exposed to air, it forms a white powder. Now that's interesting. It goes from this strip of metal to a brittle white powder, something very, very different. So I want to understand why that is. So I'm going to ask a question. So my question is, why? Why does this metal turn into a white powder? This metal was so useful. I could pound it into a sheet. It was malleable. I could pull it into a wire and conduct heat or electricity with it. It was ductile. It was very useful. And then now it's made this useless powder. So why? Why did this happen? The next step is to do some background research. And so when I do some background research, I find out that metals can react with oxygen gas in the air and undergo a chemical change. I might not understand what all of those words mean, but now that I have this information in hand, I'm ready to proceed to step 4, which is to develop a hypothesis. So before we do that, let's just be sure that we are making the connection to what we've learned. I made an observation, I asked a question, I did background research, and now I'm ready to propose a hypothesis. After that, we will design an experiment. So the hypothesis that I will test is if the metal is exposed to oxygen gas, it will form a white powder. Now, how will I test this hypothesis? Well, that's with an experiment. So here's my experiment. I will have a piece of metal and I'll put it in a chamber maybe. So here's the metal and it's magnesium metal. And in one chamber, I will have oxygen gas. In the other chamber, I will have nitrogen gas. I will predict that only the magnesium in the oxygen chamber will form the white powder. Since my hypothesis is that oxygen is necessary, it's causing this to happen. And we could have some other tests, some other trials. We could have maybe oxygen and nitrogen in this chamber, or we could have a different gas. You could use carbon dioxide in this chamber. But I'm predicting that only the metal strips in the chambers containing oxygen will react. Okay, so I could conduct this experiment and then I would think about how the results support or do not support my hypothesis. If it's consistent with my prediction here, which is that the metal only reacts in these two chambers, then it supports my hypothesis. If it's not consistent, then I would need to consider whether or not I need a different explanation for my observation or if there's a flaw in my experimental design. Let's pause for a minute to discuss variables because when we think about flaws in our experimental design, like let's say these chambers are leaky, then oxygen from the air might get in. And then you might see a reaction, say, in this chamber when you didn't expect it. But it wasn't because your hypothesis was wrong. It was because your experiment was flawed. You had an undesired gas, oxygen from the air, getting into your chamber. So let's pause for a minute and discuss variables. So you should take a minute and either look up or write down what you remember about the variables in scientific experiments. A variable is a factor, condition, or trait that can exist in differing amounts. Okay, that's very vague and universal. There's different types of variables. So there's independent variable. The independent variable is controlled by the researcher. For example, what do you think the independent variable was in my experiment? Yes, in my experiment, the independent variable was the gas in the chamber. That was controlled by me, the researcher. I decided if it was oxygen gas, nitrogen gas, a mixture of gases. The dependent variable is measured by the researcher. What did I measure in my thought experiment? Yes, so I measured whether or not the white powder was formed. Typically, the researcher thinks that the independent variable is affecting the dependent variable, and they're looking for a correlation between those variables. Now, there's one more type of variable we should consider, and that's an extraneous or confounding variable. These variables may affect the dependent variable and should be controlled or measured by the researcher. And that's because they can confuse the results. So for example, if the chamber was leaky in my example of an experiment, then I might see some unexpected results. I might see a reaction in the carbon dioxide chamber, even though I thought there was no oxygen, but there was because it was leaky. So extraneous variables or confounding variables, they may affect the dependent variable and should be controlled or measured by the researcher, just so we can keep them in mind. Now, when we write the hypothesis statement, we write if X, then Y. What do I mean by that? Well, the independent variable, this is X. Dependent variable, this is Y. So if the independent variable, then the dependent variable. So for example, if oxygen is present, then the metal will react. So if independent variable, then dependent variable. Let's think about laws and theories for a moment. So now we know how to design experiments, how to consider variables, and we've done some experimentation. So now we're communicating with other scientists, and we're communicating laws and theories. So take a moment again and pause and write down what you think laws and theories are. Laws are statements based on repeated observation. So this is related to step 1 in the scientific method. For an observation to be a law, no observations may be inconsistent. If an observation is made that is inconsistent with the law, it is no longer a law. A theory, on the other hand, is a statement that can be tested and is based on several well-established hypotheses. It provides a deeper explanation for observations and laws. So theories are explanations. They're related to step 4 of the scientific method, related to hypotheses. So laws and theories are very different. And just I want to be clear, a theory is not just some harebrained thing you come up with when you're with your friends. Theory is based on experimentation, repeated experimentation. You're not guessing. There's lots and lots and lots of evidence for theories. It's not a guess. Based on several well-established hypotheses, lots of evidence will exist. Let's think about laws for a moment, and we will look at an example. So, similar to the example that I was discussing earlier. So Lavoisier, this French scientist, conducted an experiment similar to ours, but what he did was he burned metals in a closed chamber, like we were discussing, but he measured the mass in the closed chamber before and after he reacted the metal with oxygen, because he wasn't interested in why the metal was turning into a powder. He knew. He was more interested in whether or not, like where the matter was coming from. And what he noticed is that there was no change in the mass during the reaction, which is called combustion. So the total mass before the reaction equals the total mass after the reaction. He observed this over and over and over again. And this observation is observed for all chemical reactions. And so he developed what's called the law of conservation of mass, or the law of conservation of matter, because matter gives the substance mass. So in a chemical reaction, matter is neither created nor destroyed. And this is a law. It's based on repeated observation. Now, why is that? Well, the why, the explanation for this law, would be a theory. So what theory explains the law of conservation of mass? Well, that would be Dalton's atomic theory of matter, which we will discuss later in the class. Now, I bet you're familiar with many different laws and theories. You could take a minute and pause and think about the laws and theories that you've heard of. Some common answers are Newton's laws of motion from physics. Some theories would be germ theory, the Big Bang. We can keep going. So lots of laws and theories. You can Google laws and theories in science and see if you're familiar with more of them. I bet that you are. All right, hopefully after this discussion, you have met all of our learning goals. You're definitely ready to practice. So there are some practice problems in your handout. So you should go ahead and work through them, and we'll discuss them later. If you have any questions, make sure you ask me. Be sure that you always summarize and reflect after each video lesson. So take a minute to write down what you learned today, how it relates to things that you've learned before. And I'm sure you've learned about the scientific method before, so take a minute and think about that. And then always write down what questions you have and be sure to either send them to me or bring them to office hours.